Hello, in this video we are going to examine together the central limit theorem. Recall from our previous section on sums of random variables that if variables are identically distributed, independent, and if a sufficient number of them are added together, then their sum acts like a normal distribution. More specifically, if x1, x2, xn are identical and independent random variables, then the sum, called t, of x1 plus x2 and so forth, will be normally distributed with an average value that is the sum of the expected values of each of the x's, and the standard deviation will be the root of the sum of the variances of each of these x's. Now, of course, the expected values of xk and the variances for xk are all identical to one another. Suppose x represents a quantitative variable. It could be discrete just as it could be continuous. And let us consider a scenario where a sample of n individuals is selected with replacement from a population whose average value of study is mu, and whose standard deviation is sigma for that variable. The value of x for the kth individual that will be selected is usually denoted by xk. A priori, there is no way to predict with much confidence the exact value that xk will take. However, since it comes from the population that we described earlier, its expected value is mu, and the standard deviation is sigma, in line with the parameters of the population. For example, at Marinopolis, the R-score of the student population has an average value of 29.2 with 2.8 standard deviation. Suppose that 2 students were randomly selected with replacement from the Marinopolis student population. And let's denote by x1 and x2 the R-scores that these Marinopolis students will reveal. The fact we are replacing the selected individual guarantees the independence of x1 and x2. Furthermore, since the students are to be selected from the same population, that is, the Marinopolis student population, then x1 and x2 obey the same probability distribution. And x1 and x2 are just as likely to be around 29.2, for instance. Hence, the expected values for x1 and x2 is 29.2, and the standard deviation for x1 and x2 is 2.8. Likewise, if n Marinopolis students were selected at random with replacement, then the expected value for all of these xk's would be 29.2, and the standard deviation of these xk's would all be 2.8. Now, a sample average is denoted by x bar. It's essentially the average of the n individuals that will be selected from the population. It's a random variable because the outcome of x bar depends on who is selected. In contrast, note that mu, the populational average, is not a variable. We call it a parameter, as it is not the result of chance or random selection. It consists of the average value of all individuals in the population. Now, by definition, a sample average is obtained by adding the individual results of the selected individuals divided by n. I factored out 1 over n to make this look like a linear transformation. So the expected value of x bar is the expected value of 1 over n times the sum of the x's. Properties on linear transformations allow us to factor out the 1 over n, and properties on sums of variables allow us to distribute the expected value to each of the x's. Again, since these individuals were selected from the same population, their expected values are that of the population's average. And, in the end, summing all of these mu's, n of them, multiplied by 1 over n, will give us mu. This is no surprise because we do expect that a sample average will produce something near the population's average. When it comes to the variance of the sample average, once again, properties on linear transformations allow us to factor out the 1 over n as long as it's squared. Properties on sums of variances allow us to distribute the variance to each xk. This, of course, is only valid when each of the xk's are independent. And since the variance of each xk is sigma squared, then we have n sigma squares that are multiplied by 1 over n squared and can be simplified to sigma squared over n. So if the variance of the sample average is sigma squared over n, then the standard deviation of the sample mean is sigma over root of n. This means that the variability of the sample average depends on the size of the sample as well as the variability of variable x within the population. If you prefer, a big sample will deviate very, very little from mu in general. So what do we make of all of this? So remember that when variables are identically distributed, independent, and that we have a sufficient number of variables added to one another, then the sum will act like a normally distributed variable. Well, we can apply this to the sample average as it is the result of a sum of identical variables. And therefore, x bar will obey a normal law. As we saw earlier, the expected value of x bar is mu, and the standard deviation of x bar is sigma over root of n, which justifies the parameters we're using for this normal law. This is what we call the central limit theorem, and it does apply as long as n is 30 or more. When it comes to independent selections, although in theory samples that are selected without replacement do not fulfill the criteria of independent results, we treat such cases as independent if the sample size is small compared to the population size. For instance, if the sample is less than 5% of the population size, we usually consider that as a selection with replacement, even though it might have been done without. Here's an example we had started earlier. At Marinopolis, the R-score of the student population has an average value of 29.2 with 2.8 standard deviation. Now suppose 49 students are selected at random from the Marinopolis student population. According to the central limit theorem, we would expect that this sample's average, x bar, will be normally distributed with 29.2 as its average value and 0.4 as its standard deviation. In other words, we would be very surprised that this sample of size 49 has an R-score that deviates by much more than 0.4 from 29.2. In terms of probability, for example, the probability that x bar will be above 30 is 2.275%. In other words, although a student may be very likely to have an R-score of 30 or more individually, it would be quite unlikely to select at random a sample of size 49 for which the average of this sample would be 30